Hi! In this video, let's take a look at this Kaiweets HT208D clamp meter that is capable of measuring inrush current. This meter was sent in by Kaiweets. I was told that it was released quite recently, so let's be among the first to take a closer look at its performance, and later on we will take it apart and take a look inside. Now this meter is a 6,000 counts true RMS clamp meter and can measure both AC and DC current up to 1,000 amps. A few unique features this meter offers is that most clamp meters do not have the ability to measure inrush current and noisy voltages and current readings such as those from a variable frequency drive or VFD. I will leave a product link in the video description below for those who are interested in getting one. It comes with a price tag of roughly $90, which is by no means a cheap multimeter, especially for a brand that most people probably have never heard of before. But if you need to do inrush current measurements or you need the low-pass filtering capability for measuring VFD voltages and currents, your choice is actually quite limited in this price range for a 6,000 counts true RMS clamp meter. The meter comes in with a rather nice semi-hard case with a thermocouple and a set of leads and of course some batteries to get you started. Then this meter also has a rubberized case which feels really good in your hand. Of course, I'd assume the same texture would be a magnet for grease and dirt. Well, we'll have to see in the long run how it performs. But anyway, it feels rather sturdy and can definitely take a lot of abuse. The first thing you will notice upon powering it up is the white on black backlit LCD. Some people have very strong opinion towards this kind of displays. Now, some like it, some hate it. I actually don't mind this display at all, especially given how wide the viewing angle is. Now, you can see it very well on the display here. The only angle in real life that you can't see it very clearly is the range between 10 to 15 degrees from the bottom angle this way. Now, of course, it doesn't quite show up the same way in the display, but you can see that at certain angles on the display, it started fading off. But even when I'm going this extreme angle, and you can see that the display is very, very clear. Of course, this is the angle that I'm talking about. And on this angle, you can see that it's fading away here. And another thing you might have immediately noticed is that the dual display somehow here is defaulted to temperature reading on this secondary display here. And if I just move it to different ranges, you can see that the temperature readings are here. Now, curiously enough, without the thermocouple, you wouldn't be able to measure temperature. So I'm not entirely sure why these DC displays are coming with a secondary display of the temperature here. Now, if I press function, you can see that in AC, it does come properly with a Hertz display, which is quite useful. But for DC measurement, again, it defaults to the temperature measurement. So not entirely sure why. So we will have to pop in a thermocouple to test it to actually see how it works with the temperature secondary display here. But without the thermocouple, the display is quite useless here. So now let me plug in the supplied thermocouple here and take another reading. And it appears actually the temperature doesn't quite work in this range. Let's just first turn to the temperature range here to make sure that the reading is actually correct. Yep. So in the temperature range, we can see that we do measure temperature. So let's switch back to the other ranges. And you can see that the temperature is not updating. So it appears that the temperature measurement is only working in the temperature mode. So right now you can see clearly this is 77 degree Fahrenheit that I'm holding the thermocouple here. But on the other ranges, it is not working. So now, this issue probably can be fixed relatively easily via a firmware update, but I'm just wondering who in the right mind would think it's desirable to leave a meaningless temperature reading on multiple measurement ranges without showing you any actual results here. While I'm on a rant, let me point out another thing that I don't quite like. So let me unplug these plugs and show you here. If you look at these receptacles here, both of these are red. And you will have to take another look at the labels here to figure out which probe goes where. And sometimes if you're in a dark situation, and you might not be able to see these labels very clearly. So I'm not entirely sure why they designed it this way, as it will be easily fixed by putting in a different color for different polarities here. Anyway, these are just some minor annoyances in the grand scheme of things and do not affect the performance of the meter, of course. Now, let's take a deeper look at how well it measures. Oh, by the way, one thing I forgot to mention is actually the probes are of a really, really good quality, and the silicone wires feel almost as good and as flexible as the Probe Master ones I usually use. So I like these a lot. Unfortunately, for these kind of clamp meters, you really don't get used to probe that much, but the probes are of very good quality. Of course, the test leads here, these are not gold-plated, so that would compromise the quality a little bit. But again, the cables here, these are really, really soft, so that's great. Well, I may have said it too soon. Even though the quality is great, but it doesn't really match the CAD rating here. So if you look at the meter here, the CAD rating is CAD3 1000 volts. But if you look at the probe here, not sure if you can see this at the tip here, the probe itself is rated for CAD2 1000 volts. Now, I do think that this cable and the probe is properly rated, but curious enough, this is not rated at the same rating as the meter itself. Now, to be fair, as a clamp meter, you wouldn't use the leads most of the time, so you are just going to use the meter by itself. So that, in my opinion, is just a minor thing that you need to pay attention to. If you do need to use the leads to measure high energy circuits, you certainly want to pay attention. Of course, as an Inrush meter, we're mostly interested in the Inrush current measurement, and we'll do that slightly afterwards. But first, we wanted to take a look at the other ranges to get a feel of how well this meter behaves. For the first test, let me run through some voltages with my MV216A voltage standard. So let me dial in 1 volt, 2 volts, 3 volts, 4 volts, 5 volts. And as you can see, it's largely it's accurate enough, and the speed is just as good. So let's see the range change here, 7 volts, and as it's a 6000 counts meter, it switched to a different range here, 8 volts. So by the way, this is also auto ranging, and if we're in the lower range, which I'll show you a little bit later, so now 8 volts, 10 volts, and no problem at all. So for example, if we're at 5 volts, we can also use this range button to manually dial in the range, which is very useful indeed. And also you can see here we do have the min-max, so you can use that to determine the voltage. If it's a slow changing waveform here, you can measure the min and maximum, and if you hold this, it will reset to auto. So that's all very good. And now in ohms range, this is a 100 ohm 0.01% resistor here, and last time people criticized me of holding both leads, so this time I'm just going to do it here to add some precision here. And so yeah, no problem, it's 100.1, and the reason is that there's some lead resistance, and also the tips are not gold plated. No problem at all. And one thing to notice is that the range switching is not particularly fast. In fact, I would say it's pretty slow. If you just notice it, we are turning it on, and you will see that it is relatively slow, but for a clamp meter, that is perfectly acceptable, as you would not use this to do this kind of measurement most of the time. And now let's switch to quickly to these capacitor measurement here. So let's do the capacitor, and here I have a 15,000 microfarad capacitor, and let's see how it behaves here. And I expect it to be very, very slow. Yep. Eventually, yep, 13.94, close enough. Now let's take a look at this 10 picofarad capacitor here, and let's see how it works. By the way, this one does have a rel button, so that's actually very useful, but right now it seems it's zeroed already. So let's put in this 10. And it's measuring 19. It's not superb, but let's just route it out. And let's see here. And 17. So yeah, these ones has a pretty wide range, and I'm not going to verify it. But as you can see here, we do, and we are able to measure these small capacitors as well. Now let's take a look at this white LED here. And for that, I'm going to change it to diode mode. And let's take a quick look. And as you can see here, no problem. And white LED lights up. So let me just show you one more time. No problem at all. And the forward voltage drop is 2.6 volts. By the way, while we're still here, let's take a look at the continuity test. And let's take a quick look. So that's fast enough, and but if you notice, we do have this indicator. That indicator is lagged behind quite a bit, so I'm not sure how useful that's going to be, but nevertheless, this is a very fast continuity test here. Now onto AC voltage measurement, and for that, we're going to change to AC mode. Notice that we have this VFD symbol here. That is for the low pass filtering that I mentioned at the introduction here. So that is in situations where you have this PWM signal with very high frequency content, that in order to accurately capture the voltage reading, you need a low pass filter, and which is this clamp meter that has. So let's take a look at the AC voltage measurement here. And I wouldn't expect any problem. And also you can see that we have the 60 Hertz and 120 volts. Also, you see that we have this low Z measurement here. And typically, these kind of meters has very high input impedance. And the low Z is to help you to reduce that impedance, so that when you are measuring battery voltages or some voltages, you don't get that phantom voltage reading. So let's take a look at the resistance here in this range. For that, I'm going to have the meter up here, and we'll just take a quick reading at what the input resistance is. So it looks like that is measured at around 290 Ks. And now let's take a look at the frequency measurement here very quickly. So now I'm using the WaveTech 395 to output a 1 volt peak-to-peak sinusoidal wave, and that is 1 kilohertz. Let's increase it to 10 kilohertz, no problem. And let's just go on 100, no problem. And let's go on 1 meg at a time. 1 megahertz, 2 megahertz, no problem at all. Let's see at what point does it drop out here. So right now I'm at 16 megahertz, no problem at all. 20 megahertz, it seems like it's dropping out here. 19 is no problem. 20, it is dropping out. So let's increase the amplitude to 2 volts peak to peak, and let's continue this measurement here. And typically that is, as you increase the frequency, you will need more amplitude to make it work. So yeah. So at 2 volts peak to peak, we can measure roughly 28 megahertz, and let's increase it to 5 volts peak to peak. And let's come back to the frequency here, and let's see, we can continue this. Yep. So now at 40 megahertz, there's no problem, and the 40 megahertz is the maximum I can get on this WaveTech 395 for a sinusoidal waveform output. And you can also see the duty cycle here is roughly 50%. So no problem at all. Now let's take a look at this non-contact voltage testing here. And for that, I'm moving to this range. And one thing you notice is, I'm not sure yet. So you can see that just by moving around, there's nothing nearby. You get this kind of spurious false positive readings. So let's just keep it still and moving in this socket to see if we can detect. Yep, we have no problem detecting. It just seems it's awfully sensitive. Now, it is not as useful as some other meters where you can clearly see you are closing in on a live or earth over neutral line, but this one does not have the resolution, and also is awfully sensitive. If you move it around, it definitely gives you some false positive reading. Of course, the reason you wanted to get an Inrush meter is for its inrush current measuring capability, and everything else really are just added benefits. And as you can see that this meter actually did pretty well through all the ranges, although the automatic ranging is definitely on the slower side. But again, that's not the core competency of this meter. Inrush current measurement, for those who are not familiar, is to measure the peak current when the load is first turned on, and this is important in correctly sizing the electrical circuit capacity and choosing the appropriate rated fuses for your specific applications. Any device with an electric motor and some inductive component, for instance, is notoriously known for high inrush current. And for AC applications, the maximum inrush current would not only depend on the type of the load, but also the phase of the input voltage. So it is important to be able to measure the momentary inrush to better understand the characteristics of the load. Now, the inrush current is typically measured as the maximum peak current within a predefined period of time. This meter, for example, according to the manual, is measured as the first 100 milliseconds, and you can see that they illustrated the current form here, and we are measuring the peak current in this first 100 milliseconds. Now let me hook it up with an electric drill and see what the inrush current reading is. You need to excuse me for the crude setup here, as I cannot find my line splitter, so I had to separate out the wires in order to measure the current here. So to measure the inrush current, we turn it on. By the way, this meter does come with two ranges. The first range for current is 60 and 600 amps, which is auto ranging, switching between the two. And also we have a 1000 amps range that is for higher current. So now we turn it to the 60 and 600 amps. And by default, it's a DC amp measurement, but we can press this function key and you can see switch to AC, and then hopefully the next one is for the inrush measurement. By the way, when we're cycling it through, you can see that the first one is AC, and then we have the VFD. This one is to filter out the higher frequency components of the noise when you are measuring the VFD circuits here. So now let's concentrate on the inrush current measurement. And by the way, it will be momentarily relatively loud when I turn on the drill. 3, 2, 1. So as you can see that the current reading is 15.12 amps, which is significantly higher than its running current, which is at roughly 2 to 3 amps. So let's do it again, and we should see this number change a little bit. So let's do it again, and let's run the drill here. 3, 2, 1. As you can see, this time it's slightly lower than last time. That's totally depending on the phase of your input waveform here. So this is definitely very handy when you are measuring these type of devices with high inrush current. And now let's take a look at its DC current measurement accuracy. For that, I have hooked up and turned on my Agilent 66312A power supply, and the output current right now is set as 1 amp. And so that is a fairly accurate power supply, and so we can trust that number here. Now we do have some residual values here. We're going to rail it out. So let's take a look, and as soon as I connect this, we should be getting the current reading here, and as you can see, it is really accurate relatively, and so no problem at all. And now we have tested the performance of this meter. It's time for us to take it apart and take a look at what is inside. And by the way, this meter does use 3 AAA batteries, as we can see here. And these are just what is supplied. Let's remove these, and we can take this further apart. Okay, now we're in. Let me zoom in a little bit more so we can take a closer look. And just by looking at this board, the build quality is actually top-notch, and everything seems to be very well laid out and also soldered on neatly. So let's start from the input side. And these are the two sockets I mentioned earlier, that they were both of the same color. They're both red, and you can't easily tell which one is which just by looking from the side. That said, there's not too much issue with it. And if you look at the solder point here, these are simply just secured, each of these, by one solder joint. And again, this is not the most secure connection here, but for these type of meters, usually you don't plug in your leads that many times, so this is perfectly adequate. And following this input, you will see that on the positive side, we do have two PTCs, but interestingly, there's no MOVs. So clearly, it lacks transient protection here. And also notice that we have these two resistors here in series, and essentially they're in series because this allows for higher voltages evenly distributed across these two resistors. And towards the top here, you will see that we have two back-to-back transistors serving as the input voltage clamp here. So nothing out of the ordinary. And up here, you will see that this blob is where the DMM chip is located. So because it's totally epoxied in, I have no idea what exactly that chip is. Although we don't exactly know what this DMM chip is, but it is in line with a lot of the Chinese multimeters that we have done teardown with recently. And you can see that with this companion EEPROM here. And this one is storing all the configuration and also the parameters of this multimeter. And towards the middle here, you can see this chip. Now this is a TM1622 LCD driver, which makes sense as it has LCD back there. So this is used as a dedicated LCD driver. And perhaps a little bit interesting is that even though we have this DMM chip, we also have this chip here, and this one is a HY17P48. It is a mixed signal microcontroller with an 18-bit Sigma Delta ADC here incorporated into this chip. So I would assume that some of the ADC is done within this microcontroller here rather than inside this DMM chip. And just above this HY17P48, we also have this chip here, and this is a linear regulator. The part number is XC6206, and this particular one is a 3.3 volt regulator here, and it has very low dropout voltage. So given the supply voltage is by those three AAA batteries, and in theory this regulator can be regulated and produce a regulated output even when the voltage drops to 3.6 volts. And by the way, I just did a testing by hooking up a external power supply to these two springs here, which is what is in contact with the battery case. And here is our positive, here is our negative. And I measured the quiescent current at around 30 milliamp, which is not great, but given that the backlight is always on, so that's the current, the majority of current I would assume is drawn by that LED there. And but the good news is I can lower the input voltage to actually above just below 3 volts, and the meter remains operational. Now, of course, at as I mentioned earlier, at the 3.6 is where this linear regulator drops out of regulation. So any voltage lower would mean that output from this linear regulator is unregulated. So I'm not sure in terms of the accuracy and specs what those going to be affected, how those going to be affected, but nevertheless the meter remains operational even when the battery drops to 3 volts. And towards the left here we have another 8-pin chips here, and this one is a GS8552, which is a zero drift rail-to-rail op-amp with RF filter. So this one is definitely used for amplifying the signal coming from the current sensing coil located in the jaw area. And here we also have a beeper. By looking at the hinge of this mechanism, of the jaw opening mechanism here, you will see that is everything is placed on this very thin pin here. Now I'm not sure how sturdy that pin is and how much force there is on this spring, but it does look to be relatively thin. So I wonder if it has any long-term implication here. But of course, the designer might have already put this into consideration, so this might actually be adequate. And here is the ribbon cable I mentioned earlier, that coming from the current sensing jaw into the circuit board right here, which the signal going to be amplified by this op-amp. Anyway, hope this review helps you decide whether this HT208D Inrush meter fits your specific needs. In my opinion, its build quality is excellent for its intended purpose, and its performance certainly meets its published specification for a 6,000 counts meter. I hope you liked the video. If you do like the video, please give it a big thumbs up and remember to subscribe and share. I will catch up with you next time.